Cheetahs are the fastest land animals on Earth, capable of reaching speeds up to 75 miles per hour in short bursts. Their unique anatomy, including powerful leg muscles and lightweight bones, makes them the ultimate sprinters. But what would happen if cheetahs were placed in a low-gravity environment like space? Scientists have long been fascinated by how different organisms adapt to extreme conditions beyond Earth. The idea of testing cheetahs in space may sound like science fiction, but it holds valuable implications for biomechanics and physiology. Understanding how gravity influences high-speed movement could provide insights into space travel, astronaut health, and even robotics. Space agencies like NASA have conducted extensive research on how microgravity affects human and animal movement. Previous experiments have included mice, fish, and even primates to study muscle adaptation in space. Cheetahs, with their explosive speed and specialized muscle fibers, present a unique test case for extreme locomotion. On Earth, cheetahs rely on powerful leg thrusts and flexible spines to generate speed. Their rapid acceleration comes from a combination of long limb stride and fast twitch muscle fibers. In a low-gravity environment, the reduced weight could allow them to push off with even greater force. However, microgravity presents new challenges, such as reduced traction and lack of air resistance. Cheetahs depend on friction with the ground to propel themselves forward. In space, without proper grip, their sprinting mechanics would need to adapt dramatically. If placed on the Moon, where gravity is only 1/6 of Earth's, cheetahs could theoretically achieve longer strides with less effort. This could lead to faster speeds, but also unpredictable movement patterns. Would cheetahs need to change their running technique in low gravity? Scientists hypothesize that their bodies would adjust, possibly adopting more of a bounding motion rather than a traditional sprint. Another key factor is muscle atrophy, which occurs in microgravity environments. Astronauts experience muscle and bone loss due to prolonged exposure to weightlessness. Cheetahs, despite their incredible muscular power, might also suffer from muscle degradation in space. If cheetahs could train in artificial gravity environments, such as centrifuge habitats, they might maintain their strength. Understanding how their muscles adapt could offer insights into preventing astronaut muscle loss. Another major concern is the vestibular system, which controls balance and spatial orientation. Cheetahs rely on precise coordination and quick reflexes for high-speed chases. In space, the altered gravitational field could disrupt their balance, causing disorientation. Scientists have studied how weightless environments affect human and animal balance. Previous studies on cats in low gravity showed unusual movement patterns, as they struggled to coordinate their limbs. Cheetahs, with their high-speed agility, might face even greater difficulties adjusting to new gravitational forces. Would their famed acceleration still be possible in a weightless environment? Without the downward pull of gravity, they might struggle to maintain traction, reducing their ability to generate speed. Alternatively, if placed on a treadmill within a controlled gravity setting, they could simulate sprinting on Earth. Space technology could provide a means for simulating running in different gravitational conditions. Scientists have already tested robotic exoskeletons that enhance human movement in microgravity. Similar technology could be applied to studying how cheetahs adapt their speed mechanics in space. Additionally, AI-powered simulations can model how different gravity levels affect cheetah locomotion. Using biomechanical analysis, researchers can predict how muscle forces change in different planetary conditions. If cheetahs could sprint on Mars, where gravity is about 38% of Earth's, their movement might resemble an extended leap. This could inform future research on robotic quadrupeds designed for planetary exploration. Cheetahs have specialized respiratory and cardiovascular systems that support their speed. Their enlarged nasal passages allow for rapid oxygen intake during sprints. In space, oxygen flow and circulation work differently due to the lack of gravitational influence. Would a cheetah's heart rate accelerate or slow down in microgravity? Studying their cardiovascular response could provide insights into astronaut health in prolonged space missions. Additionally, cheetahs experience extreme bursts of energy that require rapid recovery. Space-based research could determine whether recovery times change in reduced gravity environments. The concept of studying cheetahs in space is also relevant to biomimicry and engineering. Robotic systems modeled after cheetahs could improve efficiency in space exploration. If researchers understand how natural sprinters function in varying gravity, they could apply those principles to advanced robotics. Scientists are already designing quadruped robots that mimic animal movement. Cheetah-inspired robotic limbs could enhance mobility in low-gravity environments. Beyond biomechanics, studying cheetahs in space could contribute to genetic research. Cheetahs have a unique genetic makeup due to past population bottlenecks. Examining how space radiation affects their DNA could offer insights into genetic resilience. Understanding genetic mutation in space could be beneficial for long-term space colonization. If cheetah genes show unusual stability in space, they might provide clues to improving human resistance to cosmic radiation. Space agencies and conservationists could also explore preserving cheetah DNA for genetic archiving. Future lunar or Martian bioreserves might store genetic material of endangered species. If humans colonize other planets, understanding how species like cheetahs adapt to off-world environments could become important. Cheetah locomotion could even help refine exoplanet habitability models. If we can predict how Earth animals move in varying gravity, we can better assess conditions for potential alien ecosystems. Although the direct transportation of cheetahs into space is unlikely, simulated studies on Earth could yield valuable data. Testing high-speed quadruped movement in simulated microgravity could refine future experiments. Space-based biology continues to push the limits of scientific discovery. Cheetahs, as nature's fastest runners, present an exciting case study for biomechanics and space adaptation. Whether through physical tests or AI modeling, their physiology could teach us much about movement in extreme environments. The future of space research is full of unexpected possibilities. As scientists explore the effects of gravity on biological systems, cheetahs may contribute to understanding the next frontier of space travel. Perhaps one day, a cheetah-inspired robot will sprint across the surface of Mars, revolutionizing how we explore alien landscapes. Until then, the study of speed and movement in space continues to accelerate toward new discoveries.